Hi everyone, and thank you for watching this webinar that is part of a series of webinars hosted by QMEA. My name is Sylvia Clark, and I'm a Digital Technologies Enrichment Officer here at the Queensland Minerals and Energy Academy. I am joined today by my colleague Matthew Heskett, and we're also very fortunate to have Sean Collins dialing in today, who is a mine geologist with Evolution Mining at their Mount Rawdon operations. For those of you who aren't familiar with the work of the QMEA, we're part of the Queensland Resources Council, who are the peak body for the minerals and energy sector here in Queensland. With the support of our sponsors, QMEA delivers student workshops and experiences, as well as teacher professional development to the 75 schools who are in the QMEA network. The aim of today's webinar is to provide students with a look behind the scenes at how geology is used in the resources sector. So as I mentioned, we are joined today by Sean Collins, a mine geologist at Evolution Mining's Mount Rawdon operations. I'm going to hand over to Sean now to tell us a little bit more about what he does as a geologist.
Cool, thank you, Sylvia. Thank you for the introduction. So, what a geologist does. I had a look through a few of these memes, and this one I came across was the most appropriate, I think. What my friends think I do, you know, hand lens out, squatting down over a rock, trying to identify some sort of mineral. What my mum thinks I do, standing in a massive cave surrounded by perfectly formed crystals. My wife's grandmother is always asking if I've been finding any diamonds. What society thinks I do. This guy hanging off a cliff, I'm guessing I saw a few similar memes, you know, with Pierce Brosnan, out of movies like Geostorm and sort of doomsday movies, End of the Earth. What my boss thinks I do, I'm going to skip over that. What I think I do, which is, you can see there, it's at the computer and doing some sort of intricate modeling. And what I actually do, which I think most job means might end in, which sort of emphasizes the amount of communication that's required for most jobs. So that meme aside, a geologist in the mining industry tries to answer some pretty basic questions. What is it? How much is there? Where is it? Can we get it? And did we get it? So what is geology? Geology is the study of rocks. I'm sure you can find more complex definitions, but this is how I like to think of it. What they're made of, how do they form? Like most sciences, we're sort of classifying things, we're trying to understand things, but ultimately, you know, we're trying to predict and forecast things in the future. Concrete example might be, you know, we're trying to learn about certain types of deposits, ore deposits, you know, looking at plate tectonics, looking at alteration types, big regional geology. We're trying to predict and forecast places where we might get ore deposits. So geology does overlap with other fields. Chemistry, you know, you need to know about atoms, elements, things that make up rocks. Alterations, you know, what happens to minerals at certain temperatures and pressures. Physics, which comes into the sort of exploration techniques, one of which we'll touch on a bit later. Engineering, so you might be familiar with the job description geotechnical engineer. And those guys are their role is pretty much looking at rock stability and making sure it's safe. They're not just within the mining industry. You know, anytime you're sort of building something on a rock, be it a house, or you're creating some sort of underground cabin for some mining operation, you're going to be very, very interested in the safety and stability of that rock. And also astronomy. So we're looking at the formation of the elements that make up the rocks and what geological processes may have happened on other planets. So you can see here in the slide, we've got Ayers Rock. The geologist might look at that and think, what is going on here? Why have we ended up with this sort of massive protruding rock from an otherwise fairly flat landscape? Spoilers, so this is sort of an arkose sandstone. Arkose meaning that it's just rich in feldspar. And how this thing formed is 900 million years ago. There was a basin in the middle of Australia. A basin filled up with sediment. There was some uplift, some fanning, some new deposition of this arkose, this feldspar-rich sandstone, the feldspar-rich sand. And then there was burying, some compression from plate tectonics. So we're at the second last little diagram on the right-hand side of the page, and then the last diagram is, you can see this folded yellow structure in the last diagram of the page. That is sort of, and there's a small little box there. That is the arkose sandstone layer, which started off laterally but now has been folded up and is almost intersecting the surface of the Earth vertically. That is that protrusion there, and then there has been weathering and erosion around it to leave it sticking up in the landscape. So why that particular piece there is sticking up, there might be some particular nature of the feldspar there. It might be something to do with the hydrology of the area, and that might just be a higher spot on the surface. What are the main jobs of a geologist? So, just so you're interested in the field of geology, you go to university, you graduate. These are some of the things that you might find yourself doing. Most likely job prospects. It's of course if you don't choose to stay at university and continue studying. So you have exploration geologists. So these guys are going to be sort of the data collection. I mean, everything starts with exploration. You have greenfields exploration, which is a completely fresh piece of land that there is no mine site on, and you'll go in, you'll do an exploration program. On the left-hand side of the slide, you can see we've got a drill pad that has been pushed out with a dozer. So we're going to go and fit a drill rig on that pad, and it's in the middle of a sort of fairly lush green scenery, hence the name Greenfields Exploration. So this is sort of exploration where there is no mine site, you're trying to just feel out the land. We've got brownfields exploration, so this is exploration on a mine site. You're trying to stay ahead of the mine, trying to firm up the next couple of years of the mine where you're going to be mining. If you become an exploration geologist, you can expect to be looking at lots of core. Gold, if you're lucky, on the top right-hand side there, you can see some visible gold at the center of that red box, and also next to it, just a bit lower, is pyrite, which is fool's gold. And like I said, this exploration phase, and if you're an exploration geologist, you can think of yourself as a data collector. You'll be collecting lots of data. So maps, I think bottom right we've got a soil sampling program, so you can see all those data points overlaid on some geophysical image, which could be magnetics. So once your greenfields exploration is done, and you've got the thumbs up to start a mine, that's where you can, you're going to need mine geologists. So once the pit and the mine is operational, you're going to need mine geologists there. So they will sort of have a shorter term focus. There'll be some sort of plan, some sort of annual plan of the mine. You're going to produce X amount tons of coal, or certain number of tons at a certain grade, or a certain number of ounces if you're a gold mine. And so the mine geologist will be crucial to this small area grade control focus, trying to achieve that plan. So drilling holes, not spaced by tens of kilometers, but fairly closely spaced, and trying to really narrow down on the resource in that particular area. A mine geologist will also need to be versed in the extraction from the pit right through to the mill, and sometimes even transportation of the resource off-site. So at a coal mine, you'll have a coal handling and preparation plant, where they're essentially washing the coal to remove the rock, any high density material. And if you're at a gold mine, they will have a mill that is essentially just crushing, pulverizing rock to a certain size fraction, and then there'll be a chemical process to extract the gold that you have liberated. So as a mine geologist, it's good, it's quite dynamic. You need to be across a few different things, not just in your little geology space. And you also need to problem solve a lot as a mine geologist. You can see on the right hand side, so this is a pile of coal that's been essentially put on a pad waiting to be fed onto a conveyor to go to the mill to get washed. And there is an exothermic reaction that happens when you have coal with lots of pyrite in it. There is an exothermic reaction that happens where, especially after it gets wet, where that coal starts to heat up, you have that chemical reaction happening, a lot of heat being generated, and at some point you get so much heat that the coal actually catches fire. Now you can't feed that stuff onto a conveyor belt because you're going to burn through it. So sort of day-to-day problem solving, or month to month, you would sort of know, the mine geologist would be aware of what parts of what areas of the coal are pyrite rich, and that may dictate how long that we leave it sitting out on a pad exposed to the elements. Okay, and so it's almost, in the exploration phase, and once you have a mine, you're going to need these guys. You're going to need resource geologists, and that's kind of a progression from an exploration or mine geologist. This is almost like the promotion if you choose to go this way. Obviously, it involves a lot more time sitting at a computer, which, if you're like me, that was part of the reason why you got into geology, just so you weren't at a computer all day. A resource geologist is taking all that data collected from exploration, be it greenfields, be it brownfields. So, a greenfields resource geologist is building this picture, this model, trying to, almost a feasibility to see if it's worth going and starting a mine. And then brownfields resource geologist, is getting all the new information, all the new drilling that you're doing, and every year doing a model that is reported to the shareholders, and also a model that's going to provide feedback into future mine planning. So there's math at this point. A lot of it is data validation, particularly in coal. So much of the modeling is actually looking at the data, figuring out what you can and can't use. There's more math in hard rock deposits, where rather than a simple coal seam that's easy to follow underground, you've got more insidious controls on where your ore is, hard rock mineralogy. So they use something called a block model, and that's a whole field of geostatistics. So there is math. Some of it you need to know, some of it's clicking the button, but of course you need to know what math is happening when you click the button. So a resource geologist, you're ultimately going to end up with a model. You can sort of see there, you've got the layered, tiered model, which would be a stratified deposit, meaning that your resource is laid down laterally. So any sort of sedimentary environment, that would be your coal, oil, gas. And then on the right-hand side, you've got sort of a block model that's used in hard rock mining. So you divvy everything up into a block and look at a particular block and say statistically, what can we expect from this block using the drill hole information that we have. Why is geology important in mining? So I think the easiest way to break this down is to look at the mining cycle. So you start with exploration, you go to mine design and planning. At the end of exploration, is there going to be a mine, or is it just not worth it, depending on a number of factors. Then you've got the construction or development, and then you've got the production phase where you're actually extracting the resource. And then of course at the end you've got the closure and rehabilitation. So I mean, you could argue that geology is important across all these steps, but where I see the main ones is step one, the exploration. That's the geologist, the team of geologists sussing out whether this area, where is it, what is it, how much of it is there, what risks is it going to pose later down the track. So you're just collecting all this data to see whether it's worth going further. And then I'd say probably the next, from that point, there is always ongoing exploration. The more you explore, maybe the more questions you have, but you really want to try and explore the resource as much as financially possible before justifying a pit, justifying building a mine. And so then the next probably most important step for us is production. So once the mine begins, you've got that shorter interval grade control drilling, or you're shoring up what is it, how much is there, but you're doing that in a far smaller area. Essentially there's a mining schedule saying, for this year we need to be mining in this areas and we need to come up with X amount of tons. And then the mine geologist is really there to protect that schedule and look for the geological impacts that may prevent that schedule from being completed. So you're looking at geological risk management. So like I said before, you'd look at areas of high sulfur in coal, or lots of pyrite that's going to cause you problems on your storage pad. You're looking for opportunities. So once again, the geologist might be working at a coal mine and he might see an opportunity to not wash the coal if it's clean enough, or mine it in a particular way that allows you to not wash it. So there's lots of costs saved when you don't wash the coal and you can put it straight onto the train. Also looking for opportunities like say in a gold mine, areas that weren't explored in before the mining development, like in greenfields exploration, but you have a hunch that they might have a significant grade. And also in this production, this is a reconciliation, which is did we get it? So every area that you go into, you extract the resource and you compare, okay, this is what we were expecting. It's gone through the mill, coal handling preparation plant, what have you. Did we get the tons? Did we get the grade? And opportunities, maximizing the resource value. So as a geologist, you're sort of the custodian of the model and the custodian of the ore. So you need to be working with production around how to mine it, what's good practice, what's not. There's a lot of communication involved with that. And then you can see at the bottom here I've got ongoing exploration pretty much right up until the closure and rehabilitation stage. So a little bit more about myself. If you're interested in a career in geology, or you're thinking about the future, this is the path I took, maybe it'll help you. So grade 11 and 12, I did chemistry, maths B, and economics. I didn't really know at that point if I wanted to do geology, but I was definitely leaning towards something science related. And then after that, I completed a bachelor's of geology at JCU in Townsville. I didn't do any vacation work during my degree, so vacation work is, between years of your degree, you will go to a site, or you will tee up with a company that you can come out there for a number of months and work in the department that you're studying, that's relevant to your study. So I didn't do vacation work, but if you're considering a career in anything, it's good to do vacation work, because not only does it improve your employment prospects, it's looked favorably upon if you have vacation work on your resume, but for you it will provide a window into the life that you're signing up for. I might touch on that in a few slides. So after that, after my degree, I was accepted for a graduate program with Anglo-American, and I would say, so I graduated in 2011. The same reasons which initially attracted me to the profession are the same as what has kept me in the profession. So why did I choose this profession? Growing up, a lot of our family holidays were to do with the outdoors and nature, so I sort of wanted to do something with my life that was outdoors. I had a fear of having an office job, and of course at the time I graduated, there was employment opportunities and money, some practical reasons there, and a love of science probably fostered from grade 9 and 10, but on top of that, my dad was a science teacher. I don't know if that helped or was a detriment to that love. Are there downsides? Yes, you need to, as a geologist, you need to be aware of what you're signing up for. So if you go back to that first meme that I put up, you'll see what I think I do is the picture of that rather intricate model that's being done. That's what I think a lot of people, their understanding of what geology is that you graduate, you become a geologist, you might end up in some major city or some CBD punching out models. But with geology, you sort of earn your stripes on site, so typically you start remote, you stay remote for a number of years, or in regional areas, before you get that opportunity to become that resource geologist, or that specialist geologist who is sort of living in a capital city. So if you look at where I've gone, since I graduated, I was out at Middlemount, Central Queensland, Mowra, Central Queensland, and the current mine I'm working at is Evolution Mine Mount Rawdon, which is about an hour west of Bundaberg. So all regional areas. I'm coming up on 10 years in the industry. Be prepared for camp life. So in the middle photo down the bottom, you can see a camp setup, which is pretty much if you're doing FIFO, fly in, fly out, or DIDO, drive in, drive out, where you're staying in a camp. The rooms are pretty small. And also the other thing as well with geology, if you like solving for X, and you like to know exactly what's going on, be careful, because you may feel as though you never actually solve for X. Not exactly. So all models are wrong. Some are just more precise than others. And to answer that question, did we get it? Did we get what we say we were going to get? That's one of the golden gooses of mining, is a good reconciliation. My favorite part of the job, a dynamic environment. So in this current role, so I've worked in exploration before. I'm currently working as a mine geologist. So currently, my favorite part of the job is a dynamic environment. Every day the pit has changed. This is bottom left is a photo of me from the lookout, looking out at the pit. Every 24 hours I'll come in, there'll be something new, some new rock or new area that they're mining, some new place that we're drilling that requires sampling. Another favorite part is the diversity of the work you get to do as a geologist. So you're not just at the core yard, combing over thousands and thousands of meters of core and stuck to some rock with your hand lens. There's lots of other disciplines and tasks that you can do. Like you've got database geology, so you're getting enormous amounts of data. How do you store it? There's particular softwares for that. And then probably the data analysis is a part of the work that I really enjoy. So all that data that you've stored, all right, let's crunch it in a way that's meaningful and going to add value. And then the people, you live in these camps and you're all close together and there's not much space. Living regionally, you build some good friendships and there's good camaraderie brought on from the remoteness, I think. Particularly in exploration, where you have your own crews and you're all helping each other out with your individual holes. In my experience, when I did exploration geology in coal, you're given a rig and a drill hole that needs to be drilled, and you're sort of in charge of that. And you go through the site setup, you capture all the data, you bag the core, you collect all the information, and then you put a bow tie on it. You do the site rehab, and then you move on to the next hole. So everyone's helping each other out with their own areas. So I understand you guys have been looking at isotopes and radioactive decay. So I'll talk a little bit about some exploration methods that look at that radioactive decay or the energy emitted from that radioactive decay. So this particular method is called the radiometric method. So this is an exploration tool that is done aerially. So you have a plane and you have a tool or what the receptor that you're measuring the gamma rays with is on the back of the plane, and you fly a sort of grid pattern and you end up with this information. So if we just look at the picture below, you've got sort of a heat map, red areas being of high gamma energy, blue areas being of low gamma energy. So what is it? So you've got that tool, it's measuring the concentration of the radioactive elements, potassium, uranium, and thorium, by measuring the gamma rays, which are emitted from radioactive isotopes when the nucleus is unstable. So the rays can travel about 35 centimeters through rock and several hundred meters through air, hence why you're able to do this via plane, being so high up. But only 35 centimeters to rock, so you've got to think that what you're measuring, you're only measuring 35 centimeters down through the surface. So for the most part, unless outcrop, you're probably measuring what's in the soil, but that will still tell you something, because that soil has to come from somewhere, whether it's been deposited or whether it's just the degradation of the rock that is immediately beneath where that soil is now. So each gamma ray has a characteristic energy and measurement, and this allows the specific potassium, uranium, and thorium radiation to be diagnosed. So if we sort of have a look at maybe what that means from a geology perspective. You get that information, great, you've got to interpret it now. Potassium alteration, which is often associated with hydrothermal ore deposits, can be detected using the gamma ray spectrometric method. Changes in lithology or soil type are often accompanied by changes in concentrations of the radio elements. So if we have a look here, I can't show you with the pointer, but sort of in the top left of the red outline, you've got quite a red mass. Now that is one big body of granite. It's called the hogback granite, and you can see here that it's a radiometric high, and go figure. Granite is made up of lots of feldspar, which is an aluminosilicate, and there's a lot of potassium in that, so you would expect that to have a radiometric high. And if you were going to, you didn't have any drill holes, and you were going to sort of form a model of this area on very little data, you would sort of be using that as an outline. The other thing as well to consider is where this particular granite is. It's at high elevation. Probably not going to be too much soil cover, as it mostly will be eroding, or you'll have more chance of outcrop. So something to keep in mind, that would just be a little thing about the data, is less soil cover, likely to get higher readings if there is a rock, if there is an outcrop. So it's weaker at lower elevations. Once again, is that the rock types, or is that just because you've got more soil cover? And then it's less prominent in some andesitic flows and pyroclastics and the Briggs gamma diorite. So this is actually a tenement that's just to the north of us that I've been through and had a look at the radiometric data and seen what it means. So apologies if that's arcane, but that's just an example of the collection and maybe some of the analysis of the information. Certain types of granites, certain types of fractionation, which will depend, which you'll get an insight to from your uranium content. That might tell you whether you've got something or a system or an area that is conducive to gold mineralization. Measuring the same thing, measuring the gamma rays from decaying radioactive elements. This is a coal, oil, and gas application, so you can see that four-wheel drive there. At the top of it, you've got a long beam. That's a winch, and that winch is lowering a tool down the hole. And as that's lowering down the hole, you're getting, by every 3 centimeters, you're getting a reading for gamma. So what you're looking at here is coal, which is mostly carbon. You don't want there to be any clays in your coal. You want it to just essentially be carbon, clays being from mudstones and whatnot, which you'll usually find at the top and bottom of your seam. But so coal, you want low gamma signatures. Sandstones will have low gamma signatures. Your clays, mudstones, siltstones, these sort of things that have more likely to have potassium, uranium, thorium, things that you find in clays, they're going to have high gamma signatures. And you can see about, that about 3/4 of the way down, we've got this real kink in the blue line, which is our gamma line, and that is our coal seam there, fairly obviously. The other line, the red line kicking out to the right, that is our density line, so coal, high gamma, low density. Low gamma, high density, sorry. Low density and low gamma. Mudstones, high density and high gamma. So that's what I have, guys. I hope that helps. I hope that maybe has created a potential option for what you might choose to do post high school. Yeah, Sylvia, that's what I've got. Do you have any further questions for me?
I do have a couple. I have to say thank you so much for that. I think that especially so, these students are mostly in year 9, and I think that being able to really see how those different types of, especially gamma radiation, are used, kind of in the field is really valuable, because I think that sometimes it's quite hard to create that kind of visual, I suppose, or the visual relationship with what they're learning and how it can be used. So thank you. I think that was very comprehensive. We do have a couple of student questions. So the first question that I've got is, did you ever see yourself working at a mine when you were growing up?
So did you just repeat the end of that question? Did I ever see myself working at a mine?
Yeah, when you were growing up, so when you were in school.
No, like it's sort of like I wasn't thinking of mines when I chose the degree. Obviously after 1 year into the degree, you sort of start to think about, well, hang on, I've studied this, where am I going to end up? And you're either going to end up, you could end up in a drill rig in the middle of nowhere, or likely to end up on a mine site somewhere. So it's not something that crossed my mind until I started studying. Yeah.
Yeah, no, that's fair enough. I know myself, I hadn't really thought about the mining sector when I was in school, and I think that it's good, for a lot of these students to be exposed to this type of information, while they are still at school. So you spoke about, staying at the camp and things, fly in, fly out, drive in, drive out type thing. How long are your shifts, or what's your kind of work schedule?
Yeah, so bit of a breakdown. I'll answer that and a few other things. So currently I'm doing 8 on, 6 off. That's pretty common. So that's a common roster for mine geologists or mining engineers. I have in exploration, I did an 11 days on, 10 days off, which was also good. You will get, I'd say, what's fairly common for, that was in exploration. Another common exploration roster is 2 weeks on, 1 week off. So that one's a little bit prickly, especially if you have people who care about you somewhere. And as a graduate though, if you're with one of these larger companies as a graduate, I think you can be prepared that you're going to be working 5 on, 2 off, so the regular working week, and you'll be promoted, or you'll be encouraged to live in the regional area that the mine is in. And then maybe after you get off your graduate program, which some are 2 to 3 years, then you're more likely to have a roster.
Sure, yeah, that makes sense. Thank you for that. And it's good, for our students to know as well, how it might change from being in a graduate program to, your future employment. Probably this will be our last question. If you could tell people one thing about being a geologist or about geology, what would it be?
I think it is a career that gives you tremendous opportunity to travel. I think it gives you a lot of opportunity to specialize in things that aren't, necessarily just looking at a rock. So the data capture, the data analysis, you can, if rocks are your thing, you can specialize in mineralogy. you can specialize in sampling theory. There's just so many ways to go with geology. But I would say if you're scared of an office job like I was, I would say in my current role, my time is split with maybe 60% to 70% being in the office and 30% being out and about. Obviously, if you're in exploration, I'd say that's reversed. You've got 30% time in the office with your data entry and data analysis, and 70% of time out in the field, either mapping or on a rig somewhere. It's a good career, and it's been good to me.
Thank you, that's good, that's what we want to hear. That kind of concludes the formal part of the session today. So I'd just like to say a big thank you to Sean for taking the time to chat with us today. We really appreciate it, and we know the students really appreciate it as well. If you would like to learn a bit more about geology or about the resources sector in general, we've got a website called Awesome Resources, where you'll find a range of resources relating to the energy and minerals sector, and there's interactives and videos, particularly the videos about the different careers that are in the sector. So there's 20 videos on there under the careers in the resources sector section. We also have a Facebook page, Instagram account, where you can keep up to date with what's been happening at QMEA. And if you would like to learn more about QMEA, you can head along to our website that's on the screen now, www.qmea.org.au, or send us an email at info@qmea.org.au. Thank you again, everyone, for listening, and thank you again, Sean, for joining us today. And students, best of luck with the studies for the rest of the term. Thank you.